Okay, we consider calculus of the exponential function. The exponential base of the exponential function is a natural exponent called the Euler number. The Euler number is defined by the limiting value of 1 plus 1 over n to the nth power. In the limit and as n goes to infinity, this number approaches this value and it is an irrational number. Explain how to find the approximate value for the Euler number. We can make use of binomial expansion. A plus b to the nth power can be expanded as a power series in a and b, and we know the product of a's power and b's power, the sum of the two powers must be n. So the expansion runs from an integer k that runs from 0 to n. The sum of these two powers should be the same. The combinatorial factor is called the binomial coefficient. Okay, in case we have everything a, for example, the a is a single power, so the sum of these two powers are just n, and we have no b. So choosing a everywhere in the product of n a plus b, we choose a only. We have only a single case. So it is n factorial, and we choose everything a, so n factorial, and 0 factorial. It is only a single case. What happens if we choose a single b and there are n minus 1a? The case is we can choose b here, here, here. So there are n cases. The factor is we choose n minus 1 a's and only a single b. So this cancels to find n divided by 1 equals n, something like that. In this manner, binomial coefficient can be simplified as when k equals 0, then it is 1. When k equals 1, it is n. K equals to 2, we have n minus 1 divided by 2. So it is a factorial. And then n minus 1, if we choose in general k, n minus k plus 1 divided by k factorial. In this manner, we can determine the coefficients. So we can make use of this expansion formula, substituting 1 for a and 1 over n for b. Then, by definition, we take the limit as n goes to infinity, 1 plus 1 over n to the nth power. We substitute 1 for a and 1 over n for b. So we choose the power of b to be k for simplicity, and this is n minus k is always 1. So this one only contribute, and as I already told you in here, for the general binomial coefficients, we have factor of n minus 1 through n minus k plus 1 divided by k factorial. Okay, how many factors are there? It begins with n minus 0, n minus 1, until n minus k minus 1. Okay, so 0 to k minus 1 means we have 1 to k, so there are k factors. And we have k factors of n. So why don't we divide each n in this every factor? In that case, so what we have is 1. Okay, first of all, as k equals 0, this k equals 1, k equals 2, and 3, and so on. So we have found that there is no n, and cancels, n square not exactly cancels, but if you divide n minus 1 by n squared, it is n over n, and n over n minus 1 over n. So it is 1 times 1 minus n 1 over n. So as n goes to infinity, this one approaches 1. In this manner, we can simplify every factor. They converges to 1. So every term has only a numerator increasing by 0 factorial, 1 factor, 2 factor, and so on. So it can be expressed in terms of sum. The sigma notation can be used. So this natural exponent called the Euler's number is the sum of 1 over k factorial from k equals 0 to infinity. Remember, 0 factorial is defined by 1. It is not 0. What is the derivative of the exponential function? So we frequently use the exponential function in physics problem as well as the sinusoidal function. So we make use of the definition. So definition of derivative, exponential function, we insert tiny piece h to the argument and subtract it f of this and f of x divided by h, and limit goes to h goes to 0. This is the derivative. So by definition, it's written in this form. And then we use definition of Euler's number in here, and power has been changed. It's nx, nx plus h, and nx. We can factor this common factor out. In that case, what we have is remaining power subtracted by 1. As you know, this is by definition, it is 1 plus 1 over n to the n and power of x. The limit n goes to infinity. This is again e. So e to the x is factored out, and what we have to compute is the limit of this, including 1 over h. Okay, so why don't we rewrite this nh, pool nh. This replace this one as n prime, something like that. Then 1 over n is h over nh. So this is h over n prime. And this n prime, they are the same. So this one is n prime and n prime. And we can still return n prime to the expression n. So we have simplified the derivative of exponential function is exponential function multiplied by this limit. What is this limit? We can again expand this using binomial theorem. And the first term is this 1. However, we have subtracted this one. So 1 minus 1, they cancel. And then next term is n times h over n. N times h over n. The next term is n minus 1 divided by 2 factorial and this square and so on. We find that we have a single h in the denominator and this cancels and this one gives a finite value that is unity. After that, has the power that is greater than 1. So from next term on, this power of h grows up. Therefore, in the limit as h goes to 0, everything vanishes. Therefore, this factor is a trivial one. As a result, because we have factored this exponential out already, we conclude that derivative of the exponential function is the same as the exponential function itself. Why don't we rewrite this one by multiplying the differential dx both sides? Then we arrive at this kind of form. Why don't we express this one in this manner? Aha. We want to find the integral of this. If you want to find the integral of this, the result is x. Okay. By the way, why don't we write this one? Y equals e to the x. Then it is equivalent to say x equals log y. This log this is log e. Its base is Euler's number. It's a natural log. So if we make a replacement, this one becomes a dy over y equals x. What is x? Log y. So we can find the integral table for this 1 over x integral. This dummy variable, we can write it this way too. Express e to the x as a power series of x to the n. The binomial expansion can be used again with the same strategy. And exponential is given in here, and we added the multiply we have a power of x. So why don't we rewrite this one 1 over n with x and x? Because this one goes to infinity, we rewrite this one, redefine this one by n. So we have this n. What's that? In that case, we can make use of the binomial theorem and we can expand the powers of n. If we expand the powers of n, everything is the same except that we have this factor of x. And we find that every factor is 1 in the limit as n goes to infinity, and we arrive at this kind of expansion formula. It is x to the k divided by k factorial, where k runs from 0 to infinity. And this is identical to the Taylor series expansion of the exponential function. This one I already explained about the integral table by making use of the differentiation of the exponential function.